Okay students, I hope you are all well and healthy and ready to learn new things. So my name is Palak Patel. I am working in the Mahatma Gandhi Institute of Technical Education and Research Center Navsari in Civil Engineering Department. I am going to teach you the subject is design of reinforced concrete structure. And in this subject we are going to learn earthquake resistance design of building. In the previous lecture, we covered introduction as well as seismic method of analysis and center of mass and center of stiffness. We covered it all the things in earlier. Okay, you can watch earlier videos. Now in this lecture, we are going to design ductile detailing of beam, column and shear wall from IS 1893 13920 1993. Okay, so this topic is so easy. You just have to remember the clause. In the exam they ask explain the ductile detailing of beam, and you just have to write down from the IS code 13920 1993. Okay, so shall we start? Now ductile detailing as per IS 13920. So first thing, why we importance of ductility? Ductility means if a structure is sufficient ductile, it can resist unaccepted load reversal, impact, etc. Means ductile detailing, this type of detailing is used for the resist earthquake force. It's called ductile detailing. Okay. Provide extra reinforcement for resist earthquake force is called ductile detailing. Okay, if structure is ductile, the failure of structure will not be sudden. The failure of structure will not be sudden. So we have some time for the recover our livestocks, right? It allows structure as a whole to develop its maximum potential strength through distribution of internal forces, which is given by a combination of maximum strength of all components. Right? For the ductile detailing, building configuration must be simple and regular. Individual member must be designed for a ductility, and connection of other structure detail must be carefully attended. Right? This is called a ductile detailing. Now we are going to ductile detailing of beam as per IS 13920, and this question asked in summer 2019. So for the ductile detailing of the beam, we have to follow clause number 6.1, 6.2 and 6.3. You just have to read this clause number 6.1, 6.2 and 6.3. Simple method I can say, if clause number 6.1, 6.2 and 6.3. So in the exam they will ask explain the ductile detailing of beam as per IS 13920. Then you don't have to remember all the details is given here. You just have to remember the clause number. Because in the exam IS 13920 1993 is allowed. So you can write down all the clause from the IS code. Right? So first clause number 6.1. These requirements apply to frame members resisting earthquake induced forces and designed to resist flexure. The factor axial stresses on the member under earthquake loading shall not be exceed 0.1 FCK. The member shall have width depth ratio of more than 0.3. The width of the member shall not be less than 200 mm, and the depth of member should not be more than 1/4 of the clear span. Okay, these all the details are given in the IS 13920. Look at here. Here is IS 13920 1993, and here is the clause number 6.1. Okay, so here you can see all the data are width and depth ratio is 0.3. Okay, width shall not be less than 200 mm, right? and here is all the clause number 6.1, 6.2, 6.1.3, 6.1.3, 6.1.4. Okay, so there is all the clauses here, so you just have to write down these clauses in your exam. So you don't have to remember this all the conditions, right? So you can write it down all the things easily. Just remember the clause number. Now here is a clause number 6.2 for the longitudinal reinforcement. The top bottom reinforcement shall consist of at least 2 bars throughout the member length. The tensor ratio on any face at any section shall not be less than P minimum is equal to 0.24 under root FCK upon F5. The maximum steel ratio of any face at any section shall not exceed P maximum 0.025. The positive steel at a joint face must be at least equal to the half the negative steel at the face. The steel provided at each of the top and bottom face of the member at any section along its length shall be at least equal to 1/4 by maximum negative moment steel provided at the face of either joint. You don't have to remember all the criteria. You just have to remember the clause number. And by the remembering clause number, you can write down all the details. Just copied it. Okay. In actional joint, both the top and bottom bars of the beam shall be provided with anchorage length beyond the inner face of the column equal to the development length in a tension plus 10 times the diameter of bar minus a 90-degree bend. The longitudinal bar shall be spliced only if a hoops are provided over the entire splice length at the spacing not exceeded 150 mm. The lap length shall not be less than the bar development length in a tension. Within a joint, within a distance 2d from joint face, within a quarter length of the member, where flexural yielding may generally occurs under the effect of earthquake forces, not more than 50% of the bar shall be spliced at one section. These all details are given in the IS 13920. You just have to read it out. Okay. I will not explain everything. This figure is from the IS code. There is a development length plus 10 BD, LD plus 10 BD. Okay, here is a development length. Right. Clause number 6.3 for web reinforcement. Web reinforcement shall be consist a vertical hoop. A vertical hoop is closed strip having 135 hook with a 10 diameter extended, but not less than 75 mm at each end. So point this angle in this clause they can say this angle will be 135, but length will be 10 multiplied by diameter, but not less than 75 mm. Right? In compelling circumstances, it may also be made up of two pieces of reinforcement, a U strip and a cross ties. The minimum diameter of bar forming hoop shall be 6 mm. However, beam is clear span exceeding 5 mm. 5 meter. The minimum bar diameter shall be 8 mm. The spacing of hoop over a length 2d at either end of the beam shall not exceed d by 4 or 8 diameter of smallest longitudinal bar, whichever is smaller. So this is the spacing between the stirrups. The first hoop shall be at a distance not exceeding 50 mm from the joint face. Elsewhere, the beam shall have vertical hoop at a spacing not exceeding d by 2. right? Then after ductile detailing of column as per IS 13920, this question is asked in winter 2018. Clause number 7.1, 7.2, 7.3, 7.4. These clauses are for the column. So first is clause 7.1. This requirement apply to frame members which have a factor axial stresses in exceed 0.5 FCK under the effect of earthquake force. The minimum diameter of member shall not less than 200 mm. The minimum diameter of the member shall not less than 200 mm. However, in a frame which have a beam with a center to center span exceeding 4 meter, the shortest dimension of column shall not be less than 300 mm. The ratio of shortest cross section dimension with the perpendicular dimension shall preferably not be less than 0.4. Okay. So clause 7.1 for the general data. Clause 7.2 for the longitudinal reinforcement. Lapse places shall be provided only in the center half of the member length. It should be proportional to the tension splices. Hoops shall be provided over the entire splices length at spacing not exceeding 150 mm center to center. Any area of the column that exceeds more than 100 mm beyond the configured code due to architecture requirements shall be detailed in the following manner. You can see in this manner we have to provide it stirrups while some extended beyond column. In case of contribution of this area, the strength has been considered, then it will have minimum longitudinal and transverse reinforcement as per this code. So by this code you can draw this figure. Now clause number 7.3. Clause number 7.3 is transverse reinforcement. Transverse reinforcement for the circular column shall be consist of spiral or circular hoop in the rectangular column. Rectangular hoop may be used. See in figure. You can see there is a figure. So what the clause 7.3 says, there is in the circular column, the circular hoop will be provided. A rectangular column, rectangular hoop will be provided. The parallel leg of rectangular hoop shall be spaced not more than 300 mm center to center if the length of any slide of the hoop exceeding 300 mm. A cross tie shall be provided. See in figure. The spacing of hoops shall not exceed half the at least later dimension of the column except where special configuration reinforcement is provided. Now we have clause number 7.4. Special confining reinforcement. Special confining reinforcement shall be provided over the length L0 from each joint face towards mid-span and on either side of any section where flexural yielding may occur under the effect of earthquake forces. The length L0 shall not be less than larger lateral dimension of the member. Larger lateral dimension of the member. And 1/6 of clear span and 450, whichever is more. When the column terminates into the footing or mat, special confining reinforcement shall exceed up to 300 mm into the footing. Column supporting reactions from the discontinuous stiff member such as wall shall be provided with special confining reinforcement over their full length. So you can see here is a development length here. Now we have to provide a beam column joint. We have to understand why beam column joint is most important phenomena for resist earthquake force. In RC building, portion of common to beam at their intersection are called beam column joint. This is called as beam column joint. Since their constituent materials have limited strength, the joint have limited force carrying capacity. When forces larger than these are applied During earthquake, joints are severely damaged. The repairing damaged joint is difficult, so the damage must be avoided. Thus, beam column joint must be designed to resist earthquake effect. What is the earthquake behavior of joint? Or why joint is become more prominent than any other structural member during earthquake? Under earthquake shaking, the beam adjoining a joint are subjected to movement in the same direction, clockwise or counterclockwise. Under this movement, the top bar in the beam joint are pulled in one direction and the bottom bar in the opposite direction. So at the junction, we found two different types of forces in a two different direction. These forces are balanced by a bond stress development between concrete and steel in a joint region. So if column is not wide enough or if strength of concrete is in the joint is low, there is insufficient grip for concrete on a steel bar. Insufficient grip for concrete on a steel bar. In such a circumstances, the bar slip inside the joint region, and beam lose their capacity to carrying load. Further, India and the action of the above push-pull force at the top bottom end undergoes geometrical distortion, one dialogue length of a joint elongated in the other compressed. Okay, one is a tension and other is a compression at beam column joint. Now we have provided reinforcement of beam column joint. A diagonal cracking and crushing of concrete in a joint region should be prevented to ensure good earthquake performance of RC frame building. Using large column sizes in the most attractive way to achieve this. In addition, closely spaced closed loop steel ties are required around the column bar to hold together concrete in the joint region and to resist shear forces. Immediate column bar also are effective in confining the joint concrete and resisting horizontal shear forces. Providing closed loop ties in the joint required some extra effort. Sigma 13920 IS 13920 1993 recommended continuing the traverse loop around the column bar through the joint region. In the practice, this achieved by preparing a cage of the reinforcement of all beam at the floor level to prevent on the top of beam formwork to the level and lowered into cage. However, this may not always be possible, particularly when the beams are long and the entire reinforcement cage become heavy. Now you can see here. Here is a column, here is a beam, and this closed ties means this type of ties we have to provide, right? Now we are going to design a shear wall. The reinforcement concrete building often have vertical plane like RC wall called a shear wall. In addition of slab, beams and column, these were generally started at the foundation level and continue throughout the height of the building. Their thickness can be as low as 150 mm. Thickness can be low as 150 mm or high at 400 mm in a high-rise building. 400 mm in a high-rise building. Shear wall generally provided along both length and width of building. Shear wall is likely vertically oriented wide beam that carry earthquake load downward to the foundation. This of shear wall. So properly designed and detailed building with the shear wall have shown very good performance in the past earthquakes. The overwhelming success of a building with a shear wall is resisting strong earthquake in a summarize in this quota. We cannot afford a built concrete building meant to resist severe earthquake without shear wall. So we cannot afford shear wall in a high seismic region require special detailing. Shear wall are easy to construct because reinforcement detailing of wall is relatively straightforward and therefore easy implemented at site. Shear walls are efficient both in terms of construction cost and effectiveness in minimizing earthquake damage in structural and non-structural element. So these are the advantages of shear wall, right? Now we have to discuss the requirement of shear wall as per IS 13920/1993. Thickness of wall shall not be less than 150 mm. The thickness of wall shall not be less than 150 mm. Shear wall shall be provided with reinforcement in the longitudinal and transverse direction in a plane of the wall not less than 0.25% of gross area in each direction. Not less than 0.25% of gross area in each direction. If the factor shear stresses of wall exceed 0.25 FCK or the wall thickness exceeds 200 mm, the reinforcement shall be provided in two curtains, each having bar running in the longitudinal and transverse direction in a plane of the wall. The diameter of bar used in any part of the wall should not exceed 1/10 of the thickness of that part. This all requirement is given in the IS 13920/1993, clause number 9. Clause number 9. The maximum spacing of reinforcement in either direction shall not exceed the smaller of the following: LW by P 3TW 450 mm, where LW is horizontal length of wall, TW is thickness of wall wave. Nominal shear stress tau V is equal to Vu upon TW into TW. So Vu is equal to factor shear force, TW is thickness of wave, and TW effective depth of wall. So by this equation we can find out nominal shear stresses. Nominal shear stresses is used for the calculate shear check. Right? Now architectural aspect of shear wall. The shear wall should be provided along preferably both length and width. If they are provided along one direction, a proper grid of beam and column in a vertical plane must be provided along the other direction to resist strong earthquake effect. Door and window opening can be provided in shear wall, but their size must be small, ensure least interruption to force flow through wall. Moreover, openings should be symmetrically located. Openings should be symmetrically located. Special design checks are required. Ensure that the net cross section area of wall at an opening is sufficient to carry the horizontal earthquake force. Shear wall in a building must be symmetrically located in a plan to reduce ill effect of twists in a building. They could be placed symmetrically along one or both directions in the plan. Shear walls are more effective than located along exterior periphery of building, such as layout in crease resistance of building or to twisting. Okay. Now shear wall along in cross section, that is one direction of the cross section is much larger than other, while rectangular cross section is common. L and U shape section are also used. So here U is simple, here is L shape, and here is U shape. I write here C shape. Okay. Thin walled hollow RC shaft around the elevator core of the building also act as a shear wall and should be taken advantage of resistant earthquake forces. This RC hollow core around elevator. RC hollow core around elevator. Now, reinforcement bar in a shear wall. Steel reinforcement bar are not to be provided in the wall in a regularly placed vertical and horizontal grid. The vertical and horizontal reinforcement of wall can be placed in one or two parallel layers are called curtain. So one and two parallel layer is called curtain. Right? Horizontal reinforcement need to be encouraged at the end of wall. The minimum area of reinforcing steel to still be provided is 0.0025 times the cross-sectional area along each of the horizontal and vertical directions. The vertical reinforcement should be distributed uniformly across the wall section. Vertical reinforcement should be distributed uniformly across the wall section. Right? Now we have to discuss the method of improving ductility, and this question is asked in November 2016, May 2017. Structural layout should be simple and regular. Offset at a junction of the beam and column offset between two floors must be avoided. So offset must be avoided in a structural layout. Beam should be designed as a WRC beam. Beam should be designed as a WRC beam. In RC frame structure, design of beam and column shall be just such that inelasticity remain only in beam and column remain elastic. Sufficient shear reinforcement should be provided so that shear strength remain higher than flexural strength and non-ductile shear failure can be avoided. To increase the ductility of the member, closed stirrups or spirals should be provided at point of maximum bending moment. Splices and bar should be sufficient enough to prevent bond failure. Beam column junctions should be monolithic. Footing band, plinth band, sill band, lintel band, etc. should be provided in the structure. Portion between footing beam and plinth beam should be covered with brick masonry. In frame structure, shear wall should be provided near staircase. Beam should be designed as under reinforced section. Junction of beam, column and slab should be strong. Instead of long bearing structure, frame structure should be designed to increase the ductility of the structure. Right? These are the methods of improving ductility. I hope you remember all the things. Okay. Just read it out and you can write it out by your own. Now we have one example here. So let's check this example in the Word file. Okay, so here is example. Draw and detail a typical collective reinforcement detailing of two span reinforced concrete continuous rectangular beam of dimension 230 by 500 mm as per IS 13920 1993 ductile detailing provision. So this question asked in November 2016 as well as 2018. Same example. Okay. The solution is a size of beam is fixed is given. Okay, 230 by 500. Hoop spacing distance 2D near support and assume effective cover 50 mm. So these all things are assuming. Okay. Now we are going to ductile detailing for the beam. For the ductile detailing of the beam we discussed in the lecture, there is a IS 13920-1993 clause number 6.3.5. Clause number 6.3.5. So let's check what is this clause. So here is IS 13920-1993 and here is a clause number 6.3.5. The spacing of hoof over a length 2d of the either end of the beam shall not exceed d by 4, 8 times the diameter of the smallest longitudinal bar, however if that not less than 100 mm. So here is a 3 condition is given. 3 condition is given. Let's check this all 3 condition in example. There is a d is 500 minus 50 is 450 mm is effective depth, as well as we given the first clause d by 4, 450 by 4, so 112 mm, 8 mm diameter of the smallest longitudinal bar, so 8 by 60 is 128 mm and not less than 100 mm. So provide 8 mm diameter hoops at 100 mm center to center from distance 900 mm from the face of column. So first hoop shall be distance not exceeds 50 mm from the face of column. The central length of beam d minus 4d vertical hoop spacing shall not exceed d by 4, 450 by 2, so 225 mm. So provide 8 mm diameter hoop at 150 mm center to center in the center length of the beam. Right? So these are the design of ductile detailing is completed. Now we have to draw some figure here. So look at here. Is it 220 mm for full length bar, hoop 8 mm diameter, 150 mm center to center, and same here for the 2D spacing is 8 mm diameter bar at 100 mm center to center. So here is a ductile detailing of the beam is completed. Now this example is completed. Now I give you one practice example. Explain the ductile detailing of column as per IS 13920 with sketch and given various methods for improving ductility of the structure. Okay, this question you can write in from the IS 13920. Okay, and these things are given in the video lecture, so you can write it down. These are the practice questions. Okay, so my video lecture is completed. So in the next lecture we will discuss some new topics. Till then, goodbye.